Well, good afternoon. It's 12:22. Sorry, we're about 7 minutes late getting started for Calculus 3, but I'm still the only one in the room, so don't know where everybody is. Hopefully they will be getting here soon. Let me mark at least one on the roll. Daniel came in earlier this morning. So hopefully the others will be coming in sometime. Where we left off. Well, I was in the right place and turned to the wrong place. Okay. I think last time I gave you the test on Chapter 13, and that's what Daniel came by to pick up this morning. Hopefully all of you have it. We're now in 14, and we're going to get as far as we can today and Wednesday, and then you'll have the test in Chapter 14. It'll be short, hopefully very sweet, and I do need to know if any of you are graduating this term. If you are, you've got to have all things into me before or by beginning of the day, meaning 8 o'clock or 8:30 on Tuesday, because I have to have your grades in, graduating students in on by noon on Tuesday. I was thinking it was noon on Wednesday, but it's noon on Tuesday. Someone told me they checked it this morning. So anyway, just that. Also, student course evaluations are due anytime. Sooner the better. Just don't forget them before you leave to go home for Christmas. And let's see anything else. Research papers are due. By the way, in this class, I've only received 3 out of the 4 or 5 of you, so got a little over half of those. Your first test, all but 1 has come in. Second test, 3 have come in, 3 out of 5, so please get those to me. The third test I gave you last week. Hopefully you're making progress on that. And then the last test will be on this chapter here. I'll have it for you Wednesday at the end of class. So please get your work in as soon as you can, especially if you're graduating this term. If you're not, you have till the end of the day on Thursday to get it to me. You can turn it in Friday, but I won't see it on Friday because I have to be at graduation on Friday, and that's on the Birmingham West campus. I won't even be out here. Maybe get here later in the day, but in fact, I'll try to get here later in the day. But please try to get it to me by the end of business on Thursday if you can, because all grades have to be in by noon on the following Monday. Not next Monday, the one after that. Okay. We are, as I said, in Chapter 14. At least I hope that's where we are. I don't recognize this. Yeah, there it is. Okay. 14.2. Chapter 14 is multiple integration. 14.2 is double integrals in volume. And we've done example 1, and this is the verbiage at the bottom of page 979 after example 1. Let's see. Yeah. It says, in example 1, note that by using finer partitions, you obtain better approximations of the volume. That observation suggests you could obtain the exact volume by taking a limit. The limit as your partition goes to 0, partition being the longest, the largest increment in your partition. The limit as the summation of all those f of x sub I, y sub I, as I goes from 1 to n, times your delta a sub I, as that delta is approaching 0, you get closer and closer, and that limit would then be this. Precise meaning of this limit is that the limit is equal to L if for every epsilon greater than 0 there exists a delta greater than 0. This sounds familiar, doesn't it? such that the absolute value of the L, that limit, if that exists, minus the summation that produced that limit, if that can be found to be less than epsilon, for any epsilon you happen to choose, for all partitions delta of the plane region that satisfy the delta less than delta. The magnitude of your partition, the maximum partition, less than delta, and for all possible choices, x of I, y sub I, and the ith regions. So a lot of such that if for this set, it works out pretty straightforwardly that using the limit of a Riemann sum to define the volume is a special case of using the limit to define the double integral. The general case, however, does not require that the function be positive or continuous. Okay. Definition of double integral then. If f is defined on a closed bounded region R, okay, now closed meaning that you don't have any unknown boundary, okay? Closed meaning all your boundaries are well defined, okay? Bounded, that means the region R doesn't head off to infinity somewhere and never has an end to it. So bounded region R in the xy plane, then the double integral of f over that region R is the double integral of f of xy times dA, and we'll talk about the dA a little bit later, is the same as the limit as that partition approaches 0 of the summation from I to n, I equal 1 to n, of f sub x sub I, y sub I, times delta a sub I, provided that limit exists. If that limit exists, there's your double integral. If the limit exists, then f is integrable over that region R, capital R. Having defined the double integral, you'll see that a definite integral is occasionally referred to as a single integral. Oh yeah, okay. Having defined the double integral, you'll see that a definite integral is occasionally referred to as a single integral. Okay. Okay. Sufficient conditions for the double integral of f on the region R to exist are that R can be written as a union of finite number of non-overlapping subregions, okay, that are vertically or horizontally simple, and the f is continuous on that region R, okay? So, this means that the intersection of two non-overlapping regions is a set that has an area. The intersection of two non-overlapping regions is a set that has an area of 0. That's a weird way to say it, but that's true. In figure 1413, the area of the line segment common to R and R1 is 0. Okay. So R is the union of R1 and R2, but R1 and R2 intersection has to be 0. So the two regions R1 and R2 are non-overlapping. Okay. If R1 bulged into R2 or R2 bulged into R1 and they cross the boundary, no, would not be non-overlapping. That would be overlapping. A double integral can be used to find the volume of a solid region that lies between the xy plane and the surface given by z is equal to f of xy, that volume of a solid region. If f is integrable over a region R and f of xy is greater than or equal to 0 for all xy in that R, then the volume of the solid region that lies above R and below the graph of f is that double integral. Volume is double integral over R, f of xy dA. Okay. Double integrals share many properties of single integrals. Here's a few of them. If f and g are both continuous over a closed bounded region of R, region R, and let c be a constant, then the double integral of a constant times the function is the constant times the double integral of that function. The double integral of the sum or difference of two functions is the sum or the difference of the double integrals of those two functions. The double integral of a function is greater than 0 if f of xy is greater than 0. Okay? The double integral of a function xy dA is greater than or equal to the double integral over that same region of g of xy dA, then that implies that f of xy has to be greater than or equal to g of xy. If their double integrals are f is greater than g, then the function has to be greater than g. And the double integral of f of xy over the region R is equal to the double integral of f of xy dA over R1 plus the double integral of f of xy dA over R2, where R is the union of two non-overlapping subregions, R1 and R2. Basically the thing we were talking about just before this slide. All right. That was bottom of page 979. Definition was the top of 980. Volume of solid region was middle of 980, and then those properties bottom of 980. Okay. Now we're going to look at evaluating double integrals. And normally, let's see, yeah, that's what this is, evaluation of double integrals. Consider the solid region. Okay, a little bit of verbiage first. Normally, the first step in evaluating a double integral is to rewrite it as an iterated integral. To show how this is done, a geometric model of the double integral is used as the volume of a solid. Okay? So, consider a solid region bounded by the plane z is equal to f of xy, which is 2 minus x minus 2y. Okay? And the three coordinate planes shown in this figure here. Okay? Now, the three coordinate planes, xy is equal to 0, yz is equal to 0, no, let me restate that. Where x is equal to 0, that's a portion of the yz plane. Okay, that little triangular portion at the back there. This part here. Oh, there. Let me get my pen color back again. Maybe it'll be easier to see. Yeah, that portion right there is where x is equal to 0. Here's where y is equal to 0, this triangle here on the xz plane. And where z is equal to 0, that's the portion down here on the xy plane. Okay. Now, this plane z is equal to f of xy, which is 2 minus x minus 2y. That means when x and y are both 0, z is equal to 2, of course. Okay? So there it is up there. Now, when z is equal to 0, that means x plus 2y is equal to 2. And I think someone may be coming in. Good. Muhammad is here.
Started early.
What's that?
It started early.
Not early. 12:15 is when the class starts. No, it ends at 1:55, but it goes for 2 hours and 40 minutes. Yeah, so it starts at 12:15. Lights adjusted here.
No wonder it's on time. I am thinking that 12:10, but on time when I get this. I started.
Yes. Yeah, the class starts at 12:15. Always has. Okay. But I'm glad you're here anyway. All right. What we're doing, we're evaluating a double integral using this as a model here. Consider a solid region bounded by the plane z is equal to f of xy, which is 2 minus x minus 2y, and I was just describing that. And the three coordinate planes, that's x equals 0 would be the yz plane, y is equal to 0 is the xz plane, and z is equal to 0 is the xy plane. So that's what we mean by the three-coordinate plane. So it's that portion of this plane that cuts off those three planes. Okay? Now, I was saying that when x and y are both equal to 0, z is equal to 2. There we are. X equals 0, y is equal to 0. You're right up here if z is equal to 2. Okay, now when z is equal to 0, your x plus 2y is equal to 2. If this is equal to 0, move these over here. And x plus 2y is equal to 2. That would be this line right here, where z is equal to 0, x plus 2y is equal to 2. So say y is equal to 0, z is equal to 0, x equal to 2, there it is. And when x is equal to 0, z is equal to 0, then y is equal to 1. There it is. Okay? And that's the triangular slant there. That's the boundary. Okay? We're looking at the solid region bounded by that. So everything inside the purple there. Okay? Now, how are we going to evaluate that volume? Okay? What we're going to do is pick a slice here of dx. Okay, now they didn't show this really well, but let's just imagine you have a slice dx. The dx is the d is very thin. They have it almost infinitesimally thin here. That would be fine. Okay, a dx. Well, then the area of that where you have this dx located here, somewhere between 0 and 2, that dx, the area bounded here, what you have to do is project this. This is the outer one, the biggest one of those that you have when x is equal to 0. The area here would be, okay, and just look at this. When x is equal to 0, you're going from so here's this plane that I've been looking at. This one, there it is, written here. Because this line right here, x is 0, and we're going to take z is equal to 0 to 2. Y is equal to 2. No, y is equal to 1, sorry. But this line here, this, let's let z be 0, okay, and then solve y, okay. x plus 2y is equal to 2. Actually, easier to do it that way. X plus 2y is equal to 2. When z is equal to 0, this is this line right here. Okay? Solve this for y. Okay? And this will be 2y is equal to 2 minus x. Right? Subtract x from both sides. And then divide by 2. And you get y is equal to 2 minus x over 2. And that's how they get this. Okay? That is the point on this line here. So that's going to be the base of the triangle here. The height of the triangle is merely z. So this is z back here where y is equal to 0. So where y is equal to 0, z is equal to 2 minus x. Okay? So that's going to be the height. Okay? So you've got your base in terms of x, you've got your height in terms of x, and you've got your dx, of course, in terms of x. So that's going to be the little triangle, 1/2 the base times the height. That's the area of that little triangle. The thickness is dx, and you're going to integrate that dx from 0 to 2. That's the approach that we're doing here. The area of that little thing there is 1/2 this times that, base times height. Okay? Now, they're not showing it here. They're going to show that on the next slide. That's why I tried to write it all down here for you. Okay? Each vertical cross-section was taken parallel to the XZ plane is a triangular region whose base has a length of y is equal to 2 minus x over 2. Height is z, which is y is equal to 0, is at 2 minus x. That implies for a fixed value of x, any value of x between 0 and 2, the area of the triangular cross-section is 1/2 the base times the height, which is 1/2 the y times the z. Okay? Which would be this times this, 2 minus x squared over 4. Okay? That just happens to turn out this way in this problem, the way they've set it up. It won't always come out being a rule like that, but that's what it is in this case. Okay? So there's your area as a function of x, and then your thickness will be your dx. Okay? So by that formula of the volume of a solid, of known cross-section, that would be this. There's your A of x plugged in here. And you're going 0 to 2 on x, dx here. Okay? Then, I don't know why they didn't pull this outside, but they didn't. I would have. But then they did this thing raised to the 3rd power divided by 3, so that made it 12 down here. This thing to the 3rd power. And the antiderivative of this is that to the 3rd, but then you have a minus because of the chain rule here, a minus preceding that. So when you plug in a 2 here, that would give you a 0. So that goes away. Plug in a 0 here, that gives you 0 for x. That gives you and of course the first that you plug in, that's positive, but that's 0. Minus plugging in a 0, and the minus of minus gives you a plus. That'd be 2 cubed is 8 over 12. That's 2/3. So that's the volume of the solid region.
So look at how 2/3. I don't understand how they got 2/3.
How you got what?
2/3.
2/3. Okay. Do you understand down to here?
Yes.
Okay, that makes sense to you. Okay. So here's what we're going to do. This is minus 2 minus 2 cubed over 12 minus a minus 2 minus 0 over 12 cubed. Oops. Yuck. Let me clean this up just a little bit, make it a little easier to see. Okay. All right. You see what I've done there? You plug in this value here, minus is here, 2 minus 2 cubed over 12, but 2 minus 2 is 0. So this is all 0. Okay. Then you have minus because you're using this one, right? Fundamental theorem of calculus. A minus, minus a minus, that's a plus. 2 minus 0 is 2 cubed is 8 over 12, and 8 over 12 is 3 over 2. Right?
Yes.
Factor out 4. I mean 2 over 3. 8 over 12 is 2 over 3. Yeah. Okay. This procedure works no matter how a sub x is obtained, and particularly you can find a sub x by integration, as shown in figure 1415. Now, what in the world do they mean by that? Oh. Okay. that same little triangle we had there, let's go back and look at it for a moment. Go on right here, this little triangle here. The base here is always y is equal to 0. That's where it's going from. And you're going out here to this line here, and that line is where z is 0 and x. Where z is 0, that would be y is equal to 2 minus x over 2. So that's this line here is where z is equal to 0, and that would be 2x plus y is equal to 2. X plus 2y is equal to 2. Okay. And yeah, there it is. Z is equal to that. So when z is equal to 0, that then becomes, this is when y is equal to 0, and then when z is equal to 0, and you solve for y goes to, just like we did before, 2 minus x minus 2 minus x over 2. Move this to the other side. 2y is equal to 2 minus x. So this is the point there. As you're looking that way, this is what that line always is. Now you can integrate this. Here's a dx, and this is going from x equals 0 to no, this is the dy here, because this is y is equal to 0, y is equal to 2, so that's a dy. And you can do it, that triangular cross section, and integrate that. I don't see that lends any insight to it, but it is true. Okay. That is, you consider x to be a constant and integrate this thing from 0 to that. That's the place where y, the maximum y can be when z is 0. So it's doing a sub x, boy. God, this is a weird way of doing it, okay? This is your z, okay? And you're integrating from y is equal to 0. So now, before we were doing x, now we're doing y, okay? dy's. That's why I said that. Second triangle, when I looked at that, that said, no, that's no longer a dx, that's a dy. That one right there, okay? And there's your line z is equal to blah, blah, blah. So the height, the length of this is this, okay? And if you're doing dy's, and the y is going from 0 to that, that's the maximum of what it would be, okay? This is one weird way to do it. The area of that is a function of x, and we write everything in terms of x, except for this y. Okay. But this is, so y equals 0 to y is equal to that, the maximum value it can be. Then the a sub x can be gotten from doing the integral of z, but the x is counted as a constant here, okay? Y is the variable here, going from there. So with this being a constant, that's why they put this times y. This is a constant times y minus, this would be y squared. So antiderivative of minus 2y would be minus y squared. Evaluate this for y now. These are the y values. So leave this x alone. Plug this in here, and you get 2 minus x over 2, 2 minus x over 2. Okay, so that would be this 2 minus x times 2 minus x over 2 would be 2 minus x squared over 2 minus 2 minus x squared over 4, and the difference of those is 2 minus x squared over 4. So there's the other way to get this cross-sectional area. Okay. Now it says combining those results, you have the iterated integral. Okay. Now, I don't know if you remember from last time what we meant by iterated integral. You're going from 0 to some variable part here on the first integral, and then definite values on the second. And that gives you value. Now, the way they've approached it does not make it particularly clear. Okay? But here's the key. Here's your function of x, y. That's what your z was. Remember, from the very beginning, z was equal to f of x, y. That's what you go in here. And then what you do for one of the variables, okay, express, and this is for y, express the boundary as a limit in terms of x, the last variable, but that y in terms of x, and integrate from 0 to, in this case, it happens to be 0 to that. First, integrating this with respect to y only, counting x as a constant. And then once you do that, then integrate that expression of x from 0 to 2. Now, they didn't show that here. That would be the second thing you did, integrate this from 0 to 2. But if you do a substitution or whatever you want to do that, and you'll find out you do get your value that way. So this is, I think he just tried so hard to simplify it, he's made it complicated. But let's see if he can get, well, no, here. Still going with it. To understand this process better, it helps to imagine integration as two sweeping motions. For the inner integration, a vertical line sweeps out the area of cross-section, and for the outer integration, the triangular cross-section sweeps out the volume. So basically, here's what he's saying. Pick a triangle, probably that very first one, okay, and get the area of that as you're doing a dy's here. Let y go from 0 to that value in terms of x, and then let that sweep this way. Now you're integrating with respect to dx's, and you're going from 0 to 2. So that's then your final part. Every time you do that, the triangle's getting smaller and smaller, and that's what you're summing up as you go. This is sort of like the representative one that we had to begin with. So that's a sort of a good visual way to think of it. Think of, if you have a definite thing here, the integral of dy here, and express the z in terms of x and y. You can have x's in there, and the y is going from 0 to that same thing in terms of x, okay? And integrate that on the inner integral, and then the outer integral integrates in dx's and drags that along. Okay, at least conceptually that makes sense, okay? Now, that's what he spent the entire page 981 doing. Here's Fubini's theorem. It could be a potential paper topic. Remember your paper? Okay, good. Okay. Fubini's theorem, let F be continuous on the plane region R. Okay? Or R maybe is XY plane or somewhere else. Plane region R. If R is defined by A, X is anywhere from A to B, and G1 of X is less than or equal to Y is anywhere from G1 of X to G2 of X. Those are two functions of X. X is defined from A to B, where G1 and G2 are continuous on this A to B. Then the double integral across that region of f of x, y, dA, okay, that's the same as, okay, this f of x, y, whatever it happens to be, integrated first from g of x, g1 of x, and g2 of x over y's, okay? So you're integrating only with respect to y, treating x as a constant. Once you've integrated that, then plug in these values just like you do a definite integral. Whatever that antiderivative of this is, evaluated here for y minus evaluated there for y. That gives you a function of x alone because you've integrated out your y's, and then you integrate that between a and b, and that gives you your function. So if f is defined, if r now is defined rather from c to d on y, and from h of y, h1 of y to h2 of y on x, then you just flip the order and do the dx first of this f of xy. This time, holding y as a constant and integrating with respect to x. Whatever the antiderivative of this is with respect to x, evaluate that for x equal h2 minus evaluate it for x equal h1 of y. Then you get a function only of y. This will give you a function only of y, and evaluate that, integrate that between c and d, and do it that way. And whichever way you do, it should come out the same volume, or the same value, I'll say. So, let's do this first. Evaluate this. Now, they, frankly, almost have made it really complicated seeming, but it's really not, okay? So first we're going to do this on a simple rectangle, and x is going from 0 to 1, y is going 0 to 1. We're going to evaluate that, okay? And this, on this one, it really doesn't matter because there's no, this is a square region. It doesn't matter how you do it, okay? So what we're going to do here, and you tell, and doesn't matter. It's going 0 to 1 and 0 to 1 because x and y are both going that. And it's going to be 1 minus 1/2 x squared minus 1/2 y squared. And how do you want your dA to be? You got two choices. It's either dx dy or dy dx. I don't care. dx dy. Perfect. Because they both have the same limit. dx dy. Now, if one of these had been 1 to 3, then whatever you 1 to 3, that would have to be your y. And the y would go, if that was here, then the dy would go first. If it was here, then the dx would go first. It doesn't matter because they're the same limit. Okay? So let's do just the inner integral. And integrating with respect to y, with respect to x, meaning we count y as a constant. So we're going to leave the outer integral alone, that's the d0 to 1, and we'll integrate this with respect to x. So that's what's the antiderivative of 1 with respect to x. Okay. We're integrating here 1 with respect to x. What would that be? That wasn't even up there. Antiderivative of 1 is what? X. Okay? Very good. Okay? So in my bracket here, first part is going to be an x minus, what's the antiderivative of 1/2 x squared with respect to x? Over 6. Yeah. X cubed over 6 minus x cubed over 6. Okay? Minus, now, you're integrating that last term with respect to x. There's no x in there. We just treat the y as if it's a constant. So what would that be? Minus 1/2 y squared times x, right? If that was a 7, that would be a 7x. It's a 1/2 y squared x. Okay? Now, we're integrating the x's from 0 to 1. The x's from 0 to 1, because that dx represents x's. Later we'll come back and do our dy's. Okay? So this integral from 0 to 1, don't mess with that yet. Only evaluate the inside here from 0 to 1 for x. I like to write x equals 0, 1 to x equals 0. Okay? The reason I do that, just so I remember which one I'm substituting for. Okay, when x is equal to 1, what's that first term? Yeah? 1 minus 1 over 6 minus 1/2 y squared times 1, right? And then when you put a 0 in there, nothing comes out. They're all zeros, right? Okay, so this is then what we're integrating with respect to y. Okay, except before we do that, let's go on and combine these two terms. What do those become? 5, 6. 1 minus 1, 6 is 5, 6, right? Okay, so we're integrating that. I'll write it down. The integral from 0 to 1 of 5, 6 minus 1/2 y squared dy. Okay? What's the antiderivative of 5, 6? Five, 6, y. Because you're integrating with respect to y. Yeah, right. Okay. And then next one would be y cubed over 6. Perfect. We'll evaluate that from 0 to 1. Okay. 1's really the only one that's going to give us anything. What do you get there? You get, let's do the 1 first. 5, 6 minus 1, 6. And then when you put the zeros in there, you get 0 for both of them, right? Okay. So this would be 4, 6, which is 2/3. And this has nothing with the 2/3 on the last problem. It just happens to be the same answer. Don't think it would be, okay? It just happened to be, they picked a problem that would be exactly the same thing. Though they're very different shapes and everything else. Okay, that was example 2. Let's watch how they did it. Yeah, question?
What happened to the dx dy? To the dx.
The dx. We integrated the innermost integral with respect to x, and that's what we got. We did, and then with x equals 0 to 1. We just integrated that. This became an x, that became a 1/6x cubed minus 1/6x cubed. This became a minus 1/2 xy, x squared, y squared x. That's what we got to do when we integrated that with respect to x, plugged in x equal 1 to x equal 0 to x equal 1. Plug those values in, holding y as a constant, and that gave us this. So this is the result of the integration of that first dx, that first integral with respect to x. That's what this became, which ultimately was this. And then we integrated that with respect to y. So you integrate away the x to begin with, and then the y. We could have reversed them, and it would have been identical because the x's are going between the same two values, y going through the same two values. So it didn't matter which way we ordered, but it gave us the same result. Does that answer what you were asking?
After the integration of the first one, the dx, is that a minus dy, minus the other one, or is it going to be divided in?
Okay, where are you talking about? Here?
Yes.
Okay. This is what the result of this was. When you plugged in a 1, you got a 1 here, a 1/6 here, and a 1/2 y squared here. Minus, when you value 0, that's a 0, that's a 0, that's a 0. So you just wound up with the first one. Okay? You've lost all your x's because you evaluated them away. You plugged in values for x. So that left you only y's. Well, these two are both constant, so I just combined these and made it 5, 6. Okay, and now integrate this, and there was my dy from up there, and this is the thing. The inner part of that became this, which ultimately became that. Okay, and then you integrate this with respect to y. That gives you 5, 6y, and that gives you minus 1, 6y. Okay, that goes up to 3, divided by 3, and y. And then when you evaluate this from 0 to 1, the y gives you 5, 6, minus 1, 6. When you put zeros in, minus 0, minus 0. So that gave you nothing. 5, 6, minus 1, 6 is 4, 6. Which has nothing to do with the previous problem, which is also 2/3, but see why they could have given a little something different there. Okay. Got it? Got it? Okay. Now, I'm going to erase what I did, and let's see if they explain it, which they probably will, better than I did. Because R is a square, it's both vertically and horizontally simple, you can use either order of integration. Doesn't matter which. Okay? So, they happen to choose your dx's as the last value they're going to do. Choose your dy and dx by placing the vertical representative rectangle in the region. Okay. All right. So they arbitrarily, we did the other order, they do in this order. Doesn't matter. Okay. We're doing this region as a dx dy, that's your dA, and the dx is going, the dy is going from 0 to 1, the dx is going from 0 to 1. Okay? And they're first going to do they're showing the last part first. To me, I would have shown the dy first, but they didn't. But anyway, they're doing a delta x. And think about it this way. Your dy's are like this now, because this is a x and y. They're doing this part first, and then later they're going to do the dy's to go this way. Actually, you do the dy's first. So I would have done that. So this produces the following. Okay? Double integral over the region. This is your function, just like we did, dA. And we're going to split that into dy. They doing the dy first, then the dx. So dy is going 0 to 1, dx going 0. So this time they're going to integrate this with respect to y first. Just pretend that's not even there. Okay, but your x's are a constant. So when you integrate that, that'll give you a y for this, right? A minus 1/2 x squared y for that, because that's treating x as a constant. And then this will be a minus 1/6 y cubed. Okay, all right? Okay, so let's see if that's what they get. Yes, it is. They grouped these two together and just did a y there. I did a y and y there. Either way, it doesn't matter. Huh? Yeah, sort of. Okay, they combine like terms. Terms with y's and terms without y's. Okay, these aren't like terms in any other sense, but with respect to y, this is your y term, this is your constant term. So they did that. The constant term and integrated that with respect to y, that's the constant times y, and this is a y squared term, so it's y cubed over that. So that gives you that. Okay? Evaluate this from y is equal to 0 to y is equal to 1. So you're plugging in those values only for the y's, not the x. We'll do that later. Okay? And that would give you, they reverse the order of this. They rearranged it and then went back and did it. This would give you, when you plug in a y is equal to 1. And here, this will give you minus 1, 6. So 1 minus 1, 6 would be 5, 6. This one with x in it, y is equal to 1. It's just minus 1 half x squared. There's that. Okay. But this minus this is 5, 6. This gives you that. And then you put a 0 in there, everything's 0. Okay. So you aren't subtracting anything. So now you're integrating this thing with respect to x. That's a constant. So it's 5, 6x minus, again, 1, 6 x cubed. Because bump that up by 1, that makes it a 3. Divide by 3, 3 times 2 is 6. So 5, 6x minus x cubed over 6. Evaluate that from 1, 0 to 1. Plug in the 1 first. 5, 6 minus 1, 6 is 4, 6. And when you minus the 0, 0 to 0. Doesn't contribute anything. So you get 2/3. All right. Those are the really simple ones. They do get more complicated, but not really super bad. Okay. So let's see how they go. Oh, they're going to skip example 3. Isn't that nice of them? Okay. They were pointing this out to you, by the way, that formula we used, if you went back to example 1, which we did last time, there it was. Approximate the value of a solid lying between blah, blah, blah. Okay? Using a partition made up of sides who have squares whose sides have a length of 1/4. So pretty gross thing, but when we did that, if you go back and review that, remember when we did all these? Oh, what a pain in the neck it was. And we did them and we came up with a summation, and that summation was 0.672. Okay? Now we're doing it this way. Let's see. I went through it too fast. Okay. Oh, here they told us the exact value of the solid is 2/3. We got 0.672. Not bad. Now they show us what we just did is how we got the 2/3. That one. This is how you came up with the exact value being 2/3. That's how you did it. Okay. So that was example 2. Now, the difficulty in evaluating a single integral usually depends on the function f, not on the integral. It's a major difference between single and double integrals. In the next example, you'll integrate a function similar to the one in examples 1 and 2, but a change of the region produces a much more difficult integrating problem. So now it's not the function that makes the problem, it's what your region is. That may be the problem. Okay. So here, we'll do example 3 here. This could take a bit of effort. Find the volume of a solid bounded by the paraboloid. Here's your z. Z is equal to 4 minus x squared minus 2y squared. Okay? And the xy plane. So this is where z is equal to 0. So I'm going to put and z is equal to 0. That's the xy plane, but it's a lot easier to write z is equal to 0. Okay. Now, the figure is shown. You don't have a book, do you? Oh, me. This isn't as good as writing it out because no one else can see it either. But if you've got your book, people at home, this is page 983. Here's that paraboloid, this one right here, okay? And when z is equal to 0, what you have is x squared plus 2y squared is equal to 4. You can divide everything by 4. You have x over 2 squared minus y over 2, which is square root of 2 squared, is equal to 1. Okay? Okay. And that gives you your base down here is a ellipse, okay, going from minus 2 to plus 2 on the major axis. That's your x. Okay, on the y going from minus root 2 to plus root 2, that was what you got under the y. Okay. I can't hold this up much longer. But anyway, that's your how this thing looks. That's the paraboloid, okay, elliptic paraboloid. They don't say elliptic, but it is an elliptic paraboloid. And with that as its base. All right. Now, if I can be permitted to steal from that, the base down here, and I can't draw three-dimensional well at all, but the base down here is an ellipse, and this is a really ugly ellipse, okay, with the major axis here, the minor axis there. This is the x, this is the y. This is going from, because it's heading in the other direction, from minus 2 to 2 here, and minus root 2 to root 2 here, okay, as you see in your text. Okay. Now what they do, they take a dx here and run there is your first let's call it your first integral. Okay. Now that shape at the bottom is where z is equal to 0, so that would be, like I said, x squared plus 2y squared is equal to 4. And if you divide everything by 4, that gives you x over 2 squared plus y over 2 root 2 squared is equal to 1. That's how you could write that ellipse that's at the bottom. Okay? Now, since you're doing a dx, let's get the y in terms of x. Okay? Now, I'm not sure this is the best way to do it. Maybe that one would be the best one to go from. Or maybe just that would be the best to go from. So let's do 4 minus x squared minus 2y squared and solve this y in terms of x. Okay? So that would be 2y squared is equal to 4 minus x squared. Divide by 2. And y is equal to plus or minus the square root of 4 minus x squared over 2. Okay. So, you're going from minus square root of 4 minus x squared over 2 plus 4. So this is going the whole range. So there's no reason not to, let's see, where is it? I think it's okay to double from 0 to the positive. I think that works. Here's Justin. We're in section 14.2 on page 983, example 3. This is double integrals of volume. So we're doing the volume. Now this is an elliptic paraboloid, and I haven't drawn the z part here. I intended not to, but since she came in, it looks something like this, okay? So you have the ellipses all up and down that. It just makes it ugly. The z, by the way, goes up to 4, because when x and y are both 0, z is equal to 4. So here is z is equal to 4 at the top here. All right. What we're trying to do is get the area of this slice here along the dx here, okay? And the length is going from minus square root of 4 minus x squared over 2 to positive 4. There's the length. Thickness is dx, okay? And as you integrate that, you get those are the values of y, okay? So that's going to be your inner integral, okay? Now, I just don't have any room to write.
We can delete the image.
What's that?
You can erase the image.
Erase the what?
The image.
Okay, is it all right too? Okay, let's erase this part anyway. Okay. I sort of want to hang on to the bottom. Okay? Now,
Let's do the bottom on top.
what's that?
Let's do the bottom on the top corner and then we can have that.
Oh. Yeah, I see it up there. Is that what you meant? Yeah, okay. Yeah, okay. Okay. Now, all right. What we're doing, we're integrating. The volume is going to be two integrals, okay? And the region is this down here, okay? Now, we're first doing, and you're integrating this whole thing here, okay? This thing right here, 4 minus x squared minus 2y squared, okay? And they're doing it first with respect to y, and then later they'll do it with respect to x. So these are the y ones. And as we said here, the y here is going from minus the square root of 4 minus x squared over 2 to y is equal to plus the square root of 4 minus x squared over 2. That's what your y's, so you're integrating there. Then at the end, you're going to do the x's and sweep that from minus 2 to 2. Okay? Now, you first are going to integrate this in terms of y. Okay? And it will be looks like to me they've drawn it backwards. That's what you're doing. You're integrating. I probably should put it in parentheses because that makes it easier to see. That's what you're integrating, the whole function. And you're first doing the y's, and the y is going from minus this to plus that. So that's your limits on the y. And then your x is going to go from minus 2 to 2. And that's your limits there. Now there's a part of me that wants to say, but yeah, you can make this a little easier by doing a 2 in front of this, going from 0 to that, and another 2 in front of that, going from 0 to 2 there. I think you'll see it works out the same way. And I just hate evaluating it all those places since they're going to come out being the same. So if you don't mind, I'm going to do that. I'm going to put a 2 here, and they probably don't want us to, but let's go y is equal to 0 to this. We're just going to do half at a time, but then double it, okay? So the 2 there is going to double. So we're only going to do this part and then double it to get that part, okay? And then we're going to do the same thing here and go 0 to 2 and then double that to get the back half, okay? So I'm going to go 0 to 2 here. We can do this because it's symmetric, okay? But you've got a 2 in front of each of those. It's just going to make our calculations easier. Is that okay? Okay, so let's do it. Okay, leave the 2 alone, leave the first integral alone, 0 to 2, leave the next 2 alone, and let's just evaluate this integral with respect to y. This part right here is all we're doing down here. So what is the antiderivative of 4 with 4 dy? What would that be? 4 dy. We're going to put this up. First, antiderivative of 4 dy.
It's going to be y.
4y. 4y. Yeah, exactly. Okay? So that'll be a 4y. Okay? The next part, minus x squared y, because you treat the x as if it's a constant. X squared y minus 2y cubed over 3. Perfect. Right? Okay? And they evaluate that from 0 to the square root of 4 minus x squared over 2. Yuck! What an ugly, nasty thing to do, but we got to do it. This way we only do it once, okay? That's the good news. Okay, you'll do that, and then ultimately, yeah, my pen gets all tied up in a knot. Okay. And then we'll do our dx's next. So now I think I will go on and erase my base here. I know you wanted me to, but I wanted to use it for illustrative purposes there to show why I think we can get away with doing what we're doing. Doubling. Okay. All right. So for right now, we're going to leave that 2 alone. We're going to leave this integral alone. And we're even going to leave that 2 alone, and we're going to evaluate what's in here. From y, remember this is y is equal to this to y is equal to 0. The 2 out front is going to take care of the other half of it. So, notice with a 0 there, we don't have to do the second one. You don't have to do the lower integral because it's all going to be 0. That's why I did it. So this is going to be 4 times the square root of 4 minus x squared over 2, right? Just plugging in y is equal to that for the y, minus x squared times the square root of 4 minus x squared over 2, minus, 2/3 times, now, I'm going to try to make this a little easier. I hope it won't be too confusing. I'm going to split this y cubed into a y squared times a y. Is that okay? Split the y cubed. See, this y cubed right here, I'm going to do a y squared times y, right? Because that is y cubed, right? When you integrated that, that became a y cubed, right? Okay. So I'm first going to write y squared. Y squared is just lose the square root sign, right? And then y is going to be with the square root sign. Is that okay? Okay. So losing the square root sign, that's a 4 minus x squared over 2 times with the square root sign, the square root of 4 minus x squared over 2. Okay? It was a trick, sleight of hand here. Well, here the 2's go out, and you just have the other thing. Okay, like this. So now, all right. So go in the next cell. 2. Don't mess with these yet. 0 to 2. 2. Don't mess with that one yet. But now we're going to try to combine some like terms here. Okay? And I think I'm going to erase some more stuff down here because hopefully we're not going to need this. I may regret it, but I'm doing it anyway. These were just showing you why the limits were what they were. Okay. All right. Now, what I'm going to do, if it's okay with you, is factor out, because each term has that square root in it, right? So I'm going to factor that out for you. Okay? That's going to be the square root of 4 minus x squared over 2. Times. Here's a 4 from here. Here's a minus x squared from there. And here's a minus 4 minus x squared over 3. That was all that was left from this term, remember, when we factored that out. So that's going to be then what we do times our dx. All right, now that's a mess, isn't it? So let's see if we can make this a little bit cleaner, this part right here, just this part. Well, first I'm going to do, okay, just this part, okay? So let's get least common denominator of 3, so that will be, I wish I had more room. I'm going to take this part here and move it up here. Okay. That's going to be 12 minus 3x squared minus 4 plus x squared, because that minus is in front there, over 3. Is that okay? We put this over 3, that over 3, and split this into minus 4 over 3 and plus x squared. Okay. Now let's see if we can clean that up a little bit. 12 minus 4 would be 8 minus 2x squared over 3. So that's what all that part becomes. Okay. Now, what I'm going to do next, if it's okay with you, here we have a 2 outside the bracket and a 2 square root of 2 inside the bracket. So I'm going to do the square root of 2 into 2 and give me the square root of 2. And that square root of 2 I'm going to pull out here. At the same time, I'm going to take the 3 in the denominator and pull it out there. Is that all right? Getting all those constants out from in there. And I've got the 2 that's already out there. So this 2, so this square root of 2 will go, and this will be 2 root, no. Sorry. This will become simply a root 2. But then I'm going to pull the 3 out too, because, okay, all this here became this here, and pull that out. So that's going to be the 2 from here, the root 2 from there, and the 3 in the denominator, be 2 root 2 over 3 times the integral from 0 to 2 of the square root of 4 minus x cubed, that's what was left here, times 8 minus 2x squared there. Okay, I pulled everything out, dx. That's still a mess, right? An ugly, 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 ugly mess. But I think we can do a substitution and maybe clean it up a little bit. What might you want to use as your think on this for a minute before I do that? All right. Yuck. And that's not a 3, that's a 2. I can't read my writing. I was going to say, how in the world did that get in there? And it's not. That's a 2. Okay. Here's something I regretted. Let's factor out a 2 here. Making this, we factor out another 2, make that a 4, and that leaves this to be a 4 and a 1. Okay. Now with that done, I think you can see that this becomes 4 minus x squared to the 3 half power, right?
That's the square root of 4 minus x squared. Can that be
This becomes this to the 3 halves power. And this will get us right down to where they are in the book. I'm going to write it up here. I'll probably erase it down there. 4 root 2 over 3 times the integral from 0 to 2 of 4 minus x squared. See, this is to the 1 half power. This is 2 half power, so that will be the 3 halves power dx. Okay? Now, I'm going to erase this one down here because I need the room. This is exactly what we've got there, but just that's a little more concise. Okay. Now, here's their trick. Okay? I'm going to draw a little triangle over here, okay? I'm going to let that be x, that be 2, and that we don't know, okay? All right.
what happened to the 2?
Huh?
What happened to the 2 for the dy?
From the d, I multiplied it earlier. Remember, I divided that 2 that's in the denominator, root 2 here. That's where we came up with the root 2 here. It ultimately got out there. Remember, it was right there. And I said I'm going to multiply this by, this is a root 2 here. That was a 2. And when I did root 2 and a 2, that gave me a root 2.
Final answer?
This isn't final yet, but...
No, but over here, we lost these 2. What happened to these 2?
Okay, that 2 I multiplied by... Okay. Okay. We had a 2
And a 2.
root 2 over 3. Okay?
We started with 2 and a row of 2, and then so these 2 I know where it went. So when we pulled it out, when we pull out, we factored it out and we had something else.
Okay.
But this one I don't know when you lost it.
Okay, I didn't lose it. Okay, it's part of that 4. The other part of the 4 was when I've already erased it now, but when I combined those, remember I said let's factor 4 out of there too. I mean a 2 out of there too. Okay. So the 2 came from here to give us an 4 minus x squared, which was one of these, and then this 2 was there, so that gave us 4. This was our root 2, and that was our 3. Okay, so they're all accounted for. But what I'm doing here, this is rather strange, but it is legal in most states. Okay, we're going to do a substitution here, with this being a theta. Okay, and the substitution is, I think, is x is equal to 2 cosine theta. I think that's it. Okay? Because this says that x divided by 2 is equal to cosine theta. If that's the hypotenuse, and this is a right angle here. Okay? If this is theta, then cosine of theta is adjacent over hypotenuse. So it's x over 2, multiply both sides by 2, you get x equal to cosine theta. So that's going to be the substitution for how we're going to do this. Okay? It seems bizarre, but I think it'll work here. Okay? And what we got to do is do x squared would then be 4 cosine squared theta, right? You okay with that? I just squared both sides. Okay, and then 4 minus 4 cosine squared theta, that's 4 minus x squared. That would be 4 times 1 minus cosine squared theta. And that would be 4 times sine squared theta. Okay, that would be what this thing is for sine squared theta. And then we're going to raise that to the 3/2 power. Well, I'll first take the square root of it. Square root of it would be 2 sine theta. And then I'm going to cube it. And that would be 8 times sine cubed theta. Okay, so we've got 4 root 2 over 3 integral, and here's an 8, so it's going to come out here and make it a 32. Sine cubed theta all right, what I haven't done here is my dx. Dx is equal to minus 2 sine theta, right? If x is 2 cosine theta, dx is minus 2 sine theta, right? So that's that part. The dx is minus 2 sine theta d theta. I forgot to write my d theta here. Okay, but I need to change my limits as well. Let's go back to this. When x is equal to 2, then cosine theta is equal to 1, and where cosine theta is equal to 1, that would be 0, right? So theta is equal to 0, where cosine theta is 1. Okay? When x is equal to 0, then 2 cosine theta is equal to 0. And where cosine theta is equal to 0, that would be, theta would be equal to 1. Well, all right. I need to erase some more stuff. Sorry about this. I sure hope I don't need any of this again, because I'm going to be in serious trouble if I do. Okay. All right. So if we reverse the order there, it would be 32 root 2 over 3. And we reverse the order from 0 to 1, and that's going to lose the minus sign. And there's another 2 here, so that makes it 64, taking that 2 out. Okay. That goes to 64. This will be sine 4 theta d theta. Whew. Except they have it cosine 4 theta d theta. Because they did x equal to 2 sine theta. It doesn't matter, okay? I don't think it does anyway. Now, what we're going to do is go to a integration table. And I'm going to the back of the book, I think is where it is, unless it's at the front of the book. I think it's in an appendix somewhere back here of my integration tables. It's not there. So it must be the front part before the answers. They hide these things so well. Ah, there's your integration table. This is Appendix B. Interval forms involving sine or cosine. And here's the integral of sine 4 theta. Yuck. Okay. Of sine u theta is going to be minus sine cubed theta cosine theta over 4 plus, it's iterative, and this is a real pain in the neck, but it'll be 3 over 4 times sine squared theta times the integral of sine squared theta d theta. Okay, and sine squared theta is 1/2, and you go back through all that, and because we have so little time left, that's what you use. But ultimately it becomes, and they say Wallace's formula. I don't remember Wallace's formula at all, because I don't think I've ever had it, but it must be there. And you come up with 4 root 2 pi. This thing comes up to be 3 pi over 16. If you go back and plug all that in, and we just don't have time to do it, and then go back and plug in what we had already, the 3's will cancel out. The 16 will go into this 4 times, and it's 4 root 2 times pi. Okay, so 4, oh yuck. Okay, so that gave you ultimately 4 root 2 times pi. Actually, I prefer to write 4 pi root 2. That way I don't think the pi may be under the radical. But man, what a pain in the neck. But this is what these problems become sometimes. It's not the calculus that's hard, it's all the substitution. And it just really becomes a real pain. But anyway, that's how it works out. Now they did their x over here and the 2 here, and they came out with sine theta. I glanced at it and thought they were doing cosine theta, so I did it that way. It works out the same because those two intervals work out basically almost the same. They're just a little bit different from each other. Okay, so that was example 3. Sorry about the mess, but this is how these things happen sometime. That's why I'm going to give you 25 for your final exam. Okay, I'm just kidding. A little bit. Okay. That was example 3.
You're going to give somebody a heart attack like that.
All right, so let's see what goes next here. No, we still aren't anywhere close to the average value of a function. So we'll go back to and do example 4 here. All right. And by the way, if you go to larsoncalculus.com, you'll see them work this out completely. So let me do it here, but we will do what we can here. Find the volume of a solid region bounded by the surface f of xy is equal to e to the minus x squared, and the planes z is equal to 0. I can't read. Z is equal to 0. Y is equal to 0. Y is equal to x. And x equal 1. Boy, what a mess, okay, as shown in the figure. And I wish they showed the figure. But I will try to give you, and sorry folks if you're at home, I may try to draw it later, but for those people in class now, here's what we're talking about, okay? The function here is y f of xy, which is your z, is equal to e to the minus x squared, okay? Now, certainly when x is equal to 0, this is equal to 1, okay? There's no y involvement here at all. Can't hold this very well. Okay, now, y is equal to 0 is the xz plane. Z is equal to 0 is the xy plane. So those are those two boundaries. Y is equal to x. That splits the xy plane, or this quadrant, or octant, I guess you would say, in half. There's y is equal to x. So you're not doing this part over here. And then x equal 1 chops it off there. So this is a right angle here, a 45-ish type angle there, and up there. I don't want to say 45 because they're solid angles. But anyway, that gives you the wedge that you're talking about. And when x gets larger, like when x is equal to 1, this is e to the minus 1. And when e to the minus 1 is 1 over, it's about 1/3, a little bit greater than 1/3. So it's dropped down to about 1/3 here, and all along there, that's what it is, about 1/3. Okay, so it's kind of curving downward somewhat. Okay, they show it being a little weirder looking than that. Okay, now let's project that down onto the xy plane, okay? And that's what they do next. And since y is equal to 0 would be here, this is x, this is y. X equal 1 is there, and y is equal to x is here. So this is the base of that thing, okay? It's going to be a triangle there. And if you do your dx's, here, this is your dx, or delta x they call it, which is probably more correct. Where is that going from? Okay? That's going from y is equal to x to y is equal to 0. So the length of this is x. Okay? So your first integral, if you do, I'm going to write it first as a y, okay? E to the minus x squared dy, and then we'll do the dx's second, and the dx's, I can tell you, are going from 0 to 1, okay? But the first, you're going from 0 to x, because you first are going from 0 to x here, so that's the dy, y is equal to 0 to y is equal to x, okay, so that's 0 to x, dy, and then the second integral is x going from 0 to 1, and that's that. So that's what is called for here, okay? And that looks relatively straightforward, and at least to begin with, it's fine, okay? Because you have, when you're doing y, that, in fact, this does, I think, fairly nicely. 0 to 1, and when you're integrating with respect to y, this integral here is just simply e to the minus x squared y, right? Evaluated 0 to x, okay? Right? And then you find your dx out here. Well, that's an x up there, okay? That would then be the integral from 0 to 1 of x e to the minus x squared dx. Because, ooh, wait. Don't go too fast. Yeah, that's what it would be. Okay. Okay. Now, this one we can do, right? How would you do that integration? This one right here. Well, an antiderivative is basically, but you're going to need to use a technique. Because this is close to the derivative of that. Looks like a substitution. That u equals minus x squared. Wouldn't that work? The most complicated part, the innermost part of your most complicated function. E to the minus x squared is a complicated part, and the innermost part of that is minus x squared. So let's let u equal minus x squared. Then du is equal to what?
X.
Minus 2x dx. Okay? Well, I only want an x dx there, so let's divide out a minus 2. And then go have so. Yeah. I need more room. Can I go on and erase this over here? Okay, let me erase that. Let's see if we can make that work. I don't know what. Yeah, that was part of that too. Okay. All right. Now what we've got is a minus 1/2, that's, I did put my minus over here, when divided by a -2, that came out there. Whew. The integral, I'm going to change limits in a minute, but for right now, the x dx is du, and the e to the minus x squared would be e to the u, du, right? Now we've got to mess with our limits. When x was 0, u is 0. But when x is 1, u becomes -1. And that's a big boo-hiss, because we don't usually like to have the lower limit up top and the higher limit at the bottom. So let's flip that around, and that will change this to a +1/2 integral from -1 to 0, e to the u du. I think we can do that integration, can't we? That would be 1/2. What's the antiderivative of e to the u du? Easy question. Antiderivative of e to the u. E to the u. It's itself. Remember the e function. That's my favorite function. That's e to the u evaluated from -1 to 0. Okay? And that would be when u is equal to 0, e is 1. So that's 1/2 minus 1/2e. Because when you put u equal -1, that makes it e to the -1, and that moves it downstairs. So it's maybe easier to write this way. 1/2 times 1 minus 1/e. Okay, whatever that is. And is that the same thing they get? Yeah, I believe so. If you, least common denominator here is e, so that would be 1/2 times e minus 1/e, and that's, yeah, that's the same thing they get. They just wrote it very differently. Their substitution was a little bit different than mine, but it all came out the same. Okay. So whatever that turns out to be, 0.316, they say. So this is going to be, e is about 2.7, so this will be 1.7 over 2.7, and that times 1/2. I'll take your word for it. About 0.316. That sounds right. Okay? That one wasn't quite as bad as the other one. Okay? Now, they for some reason talk about integrating the other way from a delta y to begin with, and yeah, if you had done the delta y, you would have an integral of e to the minus x dx, which is not an elementary function. But the way we did it did give you that, because you did the, when you were trying to integrate this, you were integrating with respect to y, that just gave you y here, which is fine. That then introduced x, and that is the derivative of that. So yeah, the way we did it worked. The other way never would have worked. Okay. How are we doing on time? Oh, we got plenty of time, don't we? Or are we over? We're way over. I'm sorry. Yeah. Y'all have to go to physics? Yeah, well, why don't you go to physics? Sorry about that. I just get carried away. All right. We'll continue with example 5 next time. We're almost through with this section. You can do 3 or 5. They're both at Calc Chat. 3 is at Calc View. Any of the odds 7 through 11, they're all at Calc Chat. 13 or 15, or any of the odds 13 through 19, they're all at Calc Chat. 13's at Calc View. Do any of the odds 21 to 25, they're all at Calc Chat. 23 is at Calc View. Do 27, it's at Calc Chat. Do any of the odds 29 to 33, they're all at Calc Chat. I would do 35, it's a Calc Chat and View, and then try to do either 37 or 39, they're both at Calc Chat. And hold off on the rest of those. We'll try to get those later. Sorry I went over. It was just so much fun, wasn't it? Of course it was. Okay. Any questions before I end it? Okay.